Good morning, everyone. My name is Ramon Terroba, and I will now present hydrothermal activation and our route to enhance polymer foaming for biomedical application. This study formed part of the project Functional Polymeric Device using high-pressure processes for biomedical application, which has been funded by the government of Spain. This work has been carried out by researchers from the Analysis and Design of Supercritical Fluid Processes research group at the University of Cadiz. The group focuses on three main research areas: impregnation and separation, particle regeneration, and hydrothermal reaction. The latter two have contributed to this study. In this study, the effect of performing a hydrothermal treatment prior to the supercritical CO2 foaming processes is analyzed, focusing on its influence on pore size, distribution, and the development of interconnected porous network in the produced polymers. Supercritical CO2 foaming has gained increasing popularity in polymer processing due to its successful production of functional scaffolds and its ability to overcome the drawbacks associated with traditional processes using volatile organic solvents, such as difficulty in completely removing the solvent, the need for high processing temperatures, and the inadequate morphological characteristics of the resulting polymers. This process leverages the unique physical properties of supercritical carbon dioxide to generate a porous polymer structure for tissue engineering with tunable properties achieved by adjusting key foaming parameters such as temperature, pressure, CO2 contact time, and depressurization rates. The CO2-based foaming process can be divided into two main steps. The first step, the polymer is saturated with CO2, followed by an expansion step. Above the glass transition temperature, polymers can undergo plastic deformation without fracturing. During saturation, the polymer matrix swells and its viscosity decreases, enabling processing of the polymer CO2 mixture at lower temperatures. Additionally, diffusivity within the polymer is enhanced, allowing CO2 to act as a medium for incorporating additives into the polymer matrix. The polymer type, along with the applied pressures and temperatures, largely determines the amount of CO2 that can be dissolved. Once saturation is reached, a rapid pressure drop disrupts the thermodynamic equilibrium, causing CO2 to become oversaturated within the polymer. As the polymer saturates, the glass transition temperature decreases and the polymer becomes plasticized. Several polymers are widely recognized by the scientific community for their high affinity towards CO2. Among those frequently studied are polymethyl alcohol, polycaprolactone, polyvinyl acetate, polyvinyl pyrrolidone, and polylacticoglycolic acid. Polymers are extensively utilized as scaffold in biomedical applications due to their versatility and tunable properties. They play a crucial role in tissue regeneration by providing a supportive framework for cell growth and differentiation. Additionally, polymers are used in controlled drug delivery systems, enable precise release of therapeutic agents over time. Their applications are also extend to implants, packaging material for medical devices, surgical sutures, and as additives in resin formulation to enhance material performance. The supercritical CO2 foaming process enables tuning of porosity and pore size by adjusting key foaming parameters such as temperature, pressure, CO2 contact time, and depressurization gradients. However, the mechanism of pore formation involves complex modeling, making precise and predictable control over pore size and distribution in the resulting scaffold challenges. To achieve well-defined porosity and uniform pore size distribution, Various porcine agents known as porogens, such as bicarbonates, polyethylene oxide, sodium chloride, and surplus, have been investigated in supercritical CO2 forming processes. The type, concentration, and particle size of the porogens significantly influence the property of the solid form produced. Nevertheless, an additional step is required to remove the porogen, typically performed by a solvent bleaching, most commonly using water. This step can lead to a reduction in the drop load when working with drop load scaffold, as the bioactive substance incorporated alongside the porogen might be partially lost during the bleaching process. Therefore, new strategies are required to promote interconnected porous networks and achieve optimal mean pore size without the use of solid porogens and their subsequent removal. In this concept, hydrothermal treatment, which involves water at high pressure and temperature, could enhance the formation of such porous structures. First, I will briefly review the main characteristics of water under supercritical conditions to better understand the advantages of hydrothermal processes. As you may know, water exists in different phases. The phase diagram of water is shown on the screen. Beyond certain pressure and temperature threshold, specifically 221 bars and 374 Celsius degrees, which define the critical point, a new region emerged where water exhibits intermediate properties between those of a gas and a liquid. These unique properties make it suitable for carrying out specific processes. Among the properties exhibited by water under supercritical condition, we can highlight the following: density changes. As temperature increases, water's density decreases significantly. Consequently, properties that depend on density, such as solubility and the electric constant, undergo substantial variation, even with small changes in pressure and temperature. The dielectric constant decreases with increasing temperature, causing supercritical water to behave more like a non-polar solvent than a polar one. As a result, it becomes an effective solvent for organic compounds and is fully miscible with a wide range of gases, including oxygen. Conversely, the low dielectric constant renders inorganic salts practically insoluble in supercritical water, which can lead to clogging issues in the system. Additionally, the ionic product of water decreases under supercritical conditions, making it a poor medium for ionic reaction, but favoring free radical reactions. Specific heat reaches its maximum at the critical point, implying that a significant energy input is required to surpass the critical condition of water. Furthermore, supercritical water exhibits very low viscosity, comparable to that of gases, which result in hand diffusion and ion mobility coefficients. These characteristics make supercritical water an excellent medium for facilitating reaction at high rates. Therefore, water under supercritical conditions exhibits gas-like viscosity combined with liquid-like density. Under this condition, reaction occurs in homogeneous phase and can be completed within minutes. Due to these unique properties, hydrothermal processes offer several advantages over conventional treatment methods. Among the wide range of hydrothermal applications, notable processes include synthesis reactions like hydrogenation, dehydrogenation, elimination and diol reaction, hydrolysis and hydration, partial oxidation, also extraction, hydrothermal gasification, hydrothermal liquefaction, particle synthesis. Additionally, oxidative processes such as wet oxidation and supercritical water oxidation are also prominent within hydrothermal technology. In this photograph, you can see the batch reactor we have used for the hydrothermal treatment. This is the corresponding diagram of the reactor. The individual polymer studied in this work include polycarbolactone, polylactic acid, polylactic co-glycolic acid, polyvinyl acetate, polyvinyl polybutylene acetylphenate, and chitosan. Additionally, several polymer blends were investigated, such as PLGA with PSS, PBA with PBS, PCl with PBS, and chitosan with PBS. A total of 16 experimental runs were conducted, each performing in triplicate to ensure reproducibility. During this test, the hydrothermal treatment temperature was varied between 100 and 230 degrees while maintaining a fixed pressure of 25 bars and a duration of 10 minutes. For the foaming step, parameters were adjusted based on previous experience and literature data, with temperatures ranging from 40 to 70 Celsius degrees, pressure between 200 and 300 bars, and foaming duration from 30 to 16 minutes. Regarding homogeneity, the individual polymers, PCl, PBA, and PLG and PBS demonstrated notably uniform structures throughout the samples. In contrast, the polymer blends exhibited unfavorable results due to their high heterogeneity, which compromised the consistency of the porous network. Next, the expansion factor was analyzed by comparing some cases to samples under different foaming conditions alongside a control sample without hydrothermal treatment. Notably, PLGA and PBA show a significantly higher expansion factor compared to their respective samples without hydrothermal treatment, highlighting the positive effect of the hydrothermal process on polymer expansion. Subsequently, pore size was evaluated and increase in pore size was observed in PCl, PBA, and PBS, indicating a positive effect of the hydrothermal treatment on the formation of larger pores. On the other hand, microscopic analysis of the polymer blends once again revealed a high degree of heterogeneity. These findings suggest that hydrothermal treatment is not suitable for the development of combined polymer systems, as it does not favor the formation of uniform porous structures. In conclusion, the best results were obtained with PCl, PLGA, and PBA. These polymers achieve expansion factor of 231, 474, and 7.18 respectively, and pore size of 147 micrometers for PCl, 46 micrometers for PLGA, and over 500 micrometers for PBA. According to the literature, these materials have been a relevant biomedical application. PCl is suitable for bone tissue, blood vessel, and fibrous cartilaginous tissue. PLGA can be used with adult skin cells, connective tissue cells, fibrous cartilage, and bone tissue. And the last, PBA is applicable in fibrous vascular tissue regeneration. As future perspectives, it is planned to carry out biocompatibility and degradability tests, as well as the impregnation of bioactive substances into the polymer scaffolds. Additionally, a more in-depth study of the hydrothermal treatment will be conducted, focusing on the most promising polymer identified in this work: PCl, PLGA, and PBA. This it is. Thank you for your attention, everyone.